Alright, so this is a recap of week 2's homework. So we did exact equations and special integrating factors, that mu guy, and then we also did substitution, but there's like 2 types of substitution, so I'll have to do the second type next week. So these are the questions that were assigned. Alright, so we got to find out if this is separable, linear, exact, or none of these. So if it's separable, you'll be able to get like dy dx equals something that you can separate the 2 variables with. Basically, you want to have x just by itself with dx and y by itself with dy, and then you can integrate the 2. That would be separable. This one's not, but it is linear, because you can take y over the side there, and then get dy dx over here, and then you can take the 2y, so you got like y prime and a y times a function of x. In this case it's just -2, but it still works, and it's equal to a function of x, so that's linear. And if it's exact, what you can do is basically treat that as m, and then this one as n, and take m, the partial derivative of m with respect to y, and n with respect to x, and see what you get. So when we do this one with respect to y, we get -2, and when we do with n with respect to x, we get 1. And since they're not equal to each other, it's not exact. So same guy follows for this. I did the 2 partials. They're not exact because they don't equal each other. This one, this is a function of x and this is y, so this one's separable. This one's not linear, and I didn't know why at the time, but because I was thinking if I have y prime and then everything that's just y to y with no derivative, it just needs to be y times the thing that's here. So this doesn't work because it's like quadratic. So that's no good. That's why it's not there. Like, this is a function of x. This is just dy dx, but this one here is not just something times y. Anyway, so xy dy dx. Well, this is separable because you can separate the 2, get the y's on either side, and y on one side, x on the other. It's linear because in this case we've got dy dx, and then y times a function of x equals 0, or a function of x, and we can do the partials and find that they don't equal the same thing, so it's not exact. So here's what we got to do: classify it, and if it's equal, solve it. So this one's not separable because we get dy dx isn't a function of x times a function of y. So anyway, we're going to take m. It's going to be this one, and then n is going to be this one. The one that's so what you're going to do is the one that's multiplied by dx, you're going to take the derivative with respect to y, because it's kind of like I think it's called like Fubini's theorem or something. And then you basically, if you take the partial with respect to x of an equation and then partial with respect to y of that same equation, so it's like mxy, that's going to be equal to the same thing if you've done it with y and then x. So the second partial derivative when you switch variables is supposed to be the same thing. I think that's not Fubini's theorem. I forget what Clairaut's theorem. That's what it's called. Yeah. So anyway, that's the gist of this one. Anyway, we got m and n. We're going to take the 2 partials, and they're equal to each other, so it's exact. And oh no, sorry, this was the same, in the same vein as the other ones. It's the next one that is like that. So anyway, and it's not linear because you can't turn it into that form. Alright, so this is the one we want to do. So I'm going to say m is this one, and n is this guy. M of y, that just becomes 1, and then this one, n of x, just becomes, there's a single x, so it just becomes 1, so they're exact. And then, so I changed how I write this because this is when I first started doing it. So m equals that function when you take the derivative with respect to x, the big function that we're looking for. So if you integrate this with respect to x, you're going to get this, plus a function in y. And then what you can do is take the derivative of this equation with respect to y, and then compare it to n. So n is x minus 2y, so that means h prime of y is minus 2y. So if h prime of y is minus 2y, well, h of y is going to be the integral of that with respect to y. And then we go ahead and get that. And so we found that h of y is negative y squared. So this is what our function is. F is equal to this stuff. Because, yeah, like we said, f xy is x squared plus xy plus h of y. And once we found it, we just plug it in and get that. So anyway, keep going. M is going to be this guy. N is going to be this one, because this one's times dx. So my is going to be that, and it's equal to the same thing as n with respect to x. So we'll integrate m dx. That's going to be this. That's equal to f. So we got h of y, and then take f with respect to y and compare it to n. And h prime of y is that guy. Anyway, so that's the same kind of thing that we're going to keep doing over and over again. T over y dy. I'm going to say that's m. And 1 plus ln y dt, that's going to be n. So anyway, you're just going to keep doing the same thing over and over again. I'm going to try to find one where they try and trick you. Sometimes, like, when they switch variables up like this, I hate it when they treat y like x, and it's really confusing. You got to know the dependent and independent. I guess it's not too important in this case, but yeah, these are all just the same thing. So yeah, it was a lot of practice to get used to it. I don't know why, but it's quicker now. So here's the next section. So this one's not exact. Is separable, linear, exact, or having integrating factor that is a function of either x or alone or y alone. So it's not exact, it's not separable, and it's not linear either when you look at it like this. My minus nx is going to be this. So this would be like your integrating factor. So what you're going to do is you're either going to have my minus nx over n, or it's going to be nx minus my over m. And basically what you want to do is your integrating factor has to be of one variable, just a function of x, right? Or just a function of x alone, right? X alone or y alone, right? So that, and then the integrating factor mu x is going to be the exponential of the integral of this guy. So then now I have it. This one wasn't solve it was just find it if it has one. So this one isn't separable. And it's not linear because there's a y on the bottom. Yeah, no, it's just not linear. Because you can't turn it into that form. Okay, so I'm going to say m is this one, and wait, yeah, m is this one and n is this one. So we go ahead. Turns out they were exact because they equaled each other. So you don't need a special integrating factor for this one. So that's going to be m, that's going to be n. Wait, what did I say? This is linear, right? Dy dx equals this shit. Oh yeah, so I'm going to separate these two. That's a function of x, and that's y times another function of x and dy. So this one is going to be linear. It's not separable because you can't just get x by itself, I don't think. Yeah, because there's an x here. Yeah, I need to have some kind of, like, it needs to be, dy dx has to be x, a function of x times a function of y, so it's not separable. We got m and n, so these two aren't equal to each other, so not exact. So let's try and find an integrating factor. So just take my minus nx over n, and that just depends on x, so you can take the exponential of that and get mu equal to this. Okay, so this one, So I think, wait, where does this, 1 to 6, yeah, so now we're on to the ones where you have to actually solve it. So this is m, that's n. We take the second, or we take the partial derivatives, they're not the same. So we'll try this one. This one's no good because it's got y's and x's in it. This one works out because it just depends on y. So mu of y is the exponential of the integral of this stuff. So there's our special integrating factor. So now once we got this is the new technique. This is the new kind of equation. Mu times m, just regular m, dx plus mu times n dy equals 0. Because this factor is what's required to make that relationship true. So what we're going to do is mu times that, because mu is what? Y to the minus 4. So we took m, which was 2 times xy, and divided by that, and that must have been n. So then what we're going to do is, oh yeah, I used Rojas's notation and put an m hat. That's going to be mu m. So anyway, so we've got this. So f is going to be the integral of this with respect to x. And then so when you get f, there's going to be an h of y, and then it's the same thing that we did before. So the only thing that's really different is that when it's not exact, if you can make it exact by taking these and seeing what you get, if you get something that depends on just x or just y, then you've got your integrating factor that you need to solve this. And then you can go ahead and plug it in and then compare, right? So this is f, so let's take f of y. H prime of y is going to be y squared over y to the 4th, so it's 1 over y squared. And then you can integrate that and get that, so then you take that and add it to this, replace h of y with that, so there's f. So exact same thing here. Let's call that one m, let's call that one n. They're not equal, not exact, so my minus nx is going to be this, depends on just x, so let's integrate that, and for e to that power is going to be that, so there's our integrating factor. Now we'll multiply that by m dx and n dy, and right, I had to put m and n hat, and then we're gonna integrate that with respect to x. We'll get that, but we got h of y, so then take that with respect to y and compare it to n, see what you get. Now this one, h prime of y, there's nothing in n like that, so it's 0. So when you integrate it, it was just some constant. So that's how you do that one. 11, not exact. Anyway, that's no good because it's x's and y's. That one's good. Let's integrate that. Mu m, mu n. So let's integrate that with respect to x. We got that. And compare those two. Turns out h prime and y was still 0, and same thing. And I didn't bother with this. So, because I needed to move on to the next section. So, okay, so this one, what we're kind of doing is we're doing a substitution. It's like U substitution almost. I keep using V here. I don't know why I found this harder than I did. Like, I found this hard when I did it, but it's really not that bad. So anyway, dy dx. What we want to do is we want to see if we can turn this into something that, well, get dy dx and see if you can find something common to it. This one wanted us to use x over y, or sorry, y over x rather, and do this substitution. So if v equals y over x, and then y equals this, because you're trying to find something you can plug in for dy dx. So then that's this shit, right? It's implicit. So you get that. And then I've got it in the form of v plus v squared. Now if you got a v here and a v here, you can go ahead and cancel those out. So this one is separable now, right? So now we can integrate this on both sides, and we'll get this. So that's how you do that one. This one still wants y over x, so we're just trying to rearrange. So in this one we divided by x squared, so we get minus 1 on the bottom, and then we get, well, v squared, and then this one's going to be minus v, right? And then I just write this out again just because I needed practice. So we got that and this. The V's cancel. We get that. You can flip those around, and then we get that. So I don't think I didn't finish this in time for the recitation. So that was like week 2 of Cal 3.